So, good morning. I would like to thank Elisa and the organization for inviting me to present my work, the research we've been doing for more than 20 years. And the title of my talk is Tsunamis along the Azores-Gibraltar plate boundary. So, what is our problem? We need to understand the western segment of the Eurasia-Nubia plate boundary to quantify seismic and tsunami hazard in the area. The method we use, we collected tsunami data, that means wave heights, observations and travel times, to better constrain seismic events that have poor or non-instrumental data. We know that the large earthquakes in the area triggered measurable tsunamis, and then we'll go through the results and open questions. So let's start with the problem, understand the plate boundary to quantify seismic and tsunami hazard. We know that the segment of the Nubia-Eurasia plate boundary between the Azores on the west, I think it's working, okay, and the Strait of Gibraltar has been the set of some tsunamigenic earthquakes that we can see. They start here on 1752, 1755, 1761, three events in the 18th century, and then in the Azores, the 1939, 1941, 1969, and 1975. So the tectonic regime changes from extensional close to the mid-Atlantic ridge and changes to compressional close to Iberia. Between 24 and 20 west, this linear part of the plate boundary, we call it, it is a strike-slip fault called the Gloria fault. Towards Gibraltar, we have all this diffuse seismicity, so the plate boundary is not clearly defined. If we accept that Nubia approaches Eurasia at approximately 4 millimeters per year, we would expect a magnitude 8 every 450 years and a magnitude 8.5 every 2,000 years. That corresponds to an event similar to the 1755 Lisbon event. So, the historical earthquake and tsunami catalogs for the Iberian Peninsula report events since the year 60 before Christ, and the geological record includes events from 40,000 years before present. The problem is that the location of most of these events is uncertain. So in this study, we do not include the 60 BC. The only thing we know is that, or the reports only mention an earthquake that flooded the coast of Portugal and Galicia. So we put it here, but we don't know where it is. We have the 382 AD. The documents report that some islands offshore Cape San Vicente, they disappeared. The 1929, it is the Grand Banks tsunami. There was an earthquake of magnitude 7 that generated a landslide, and this event was clearly recorded in the Azores and in the north of Portugal. The 1930 in Madeira, here, corresponds to a subaerial landslide that killed 20 people that were on the beach. The 1531 and the 1926 occurred inside Tagus estuary, and these two events, the 1939 and 1980, they are related to the Azores system, so they are out of the scope of our study. However, we have three events in the 18th century, again, the 1722, 1755, and 1761, and in the 20th century, 1941, 1969, and 1975. We don't know why we do not have any events in the 19th century. I'm not sure. Okay. So what we do, we collected all tsunami information for these events to better constrain the seismic location and to add some constraints on the focal mechanisms of these events. So what are the data that we use? We collect tsunami travel time observations and wave height observations for the historical events, and for the instrumental events that occurred in the 20th century, we use the digitized and filtered tsunami records to isolate the tsunami signal. And we use three approaches. We do the inversion of the tsunami travel times that is based on the reversibility of the linear propagation of the tsunami, that uses the tsunami travel times observed along the coast, and we use each station as a possible tsunami source, and we propagate the tsunami from that point for a time t equal to the time to the travel time observed at that station. The location of the tsunami source is this area here in red, corresponds to the minimum of the average travel time square errors in the least square sense, and the spatial distribution of this misfit is given by this equation, where TO is the observed travel time and TP the predicted travel time. Of course, this minimum is never zero, because we have instrumental events, because the source, we are using a point source, and the source has a finite extension, and due to the nonlinearity of the tsunami propagation. The second method is in use in most operational tsunami warning centers, consists in solving the Navier-Stokes equations for the continuity equation and the momentum equation using the shallow water approximation. So the numerical codes solve both linear and nonlinear equations and are currently implemented in most operational tsunami warning systems. So we need to initialize the model, and for that we need a condition for the displacement and a condition for the velocity field. For the displacement, we use the free surface deformation of the ocean, assuming that it equals the static deformation of the seafloor. This is computed using the Mansinha and Smiley equations, or also called the Okada equations, and of course, we assume that the water is an incompressible fluid. And at time t equals 0, the velocity field is 0. And the third method consists for instrumental events where the data is of good quality or more or less good quality. This consists in the inversion of the tsunami waveform to estimate the initial sea surface displacement. As I said, for earthquake-induced tsunamis, we assume that the initial sea surface displacement mimics the elastic sea bottom deformation. So if we are able to invert for the initial elevation, we can have some information on the focal mechanism. To do that, we use this equation. This is the observed waveform at each state station. We use the empirical green functions to do a fast computation of the tsunami waveforms, and we multiply this by the initial elevation. So if we invert this equation and compute this vector here, we will obtain the initial elevation at each point of the source. So we did this only for one event, because most of them we do not have good quality data. So let's go through the events that triggered measurable tsunamis. We start with the 27 December 1722. This was a medium earthquake that occurred here in the, I don't see the light, in the south coast of Portugal, close to the town called Tavira, close to the eastern end of the Azores-Gibraltar segment in the interplate domain. And the earthquake was felt as far as Lisbon and Sevilla, and it was probably generated by an offshore fault. The report say that in Tavira the quake ended with a horrible thunder, and that in the river the water split apart and ships were left dry for a long time. This is an 18th century source, so written 30 years after the event. The flooding of the city of Tavira remained in the public memory for a long time, so every year there was a procession in thanksgiving for the fact that the waters had not entirely submerged the city. So for this event, we do not have travel times and we do not have wave heights. So the only thing we could do was to run the tsunami nonlinear shallow water code to select among a set of offshore faults the one that generates a tsunami radiation pattern, that are these draws that are shown here on the right, that is focused only in Tavira. And with that, we selected an offshore fault located here. The link with this event, with all the others, and the plate boundary is still to be discussed. We move to the November 1st, 1755. This is probably one of the best documented historical events, not only in this area, but also in the world. So there are many reports on this event. The estimated magnitude varies between 8.5 and 9. The associated tsunami impacted the coast of southwest Portugal, Morocco, and the Gulf of Cadiz, where the run-up heights reported to have reached 5 to 15 meters. This transatlantic tsunami reached as far as the UK, the Caribbean islands, and North Brazil, and we have now a collaboration with some colleagues in Brazil and geologists from the University of Lisbon that we did the tsunami, we ran the tsunami propagation model, and they are looking for sediments on the north coast of Brazil, and apparently they found something. We hope to write a paper on that soon. So, for the earthquake source, the investigations on the source of the Lisbon earthquake used macroseismic data. Martinez Solares, that is in this room, published this isoseismal map. Agnès Levray from Morocco published this, the isoseismic map on the right. And Johnston in 1996 made a scale comparison with the 28th February 1969. But all these were based on comparison with the earthquake. So back in 1992, we had an historian lady working with us, and she went to the National Archives, and she did a systematic study of all the historical records that mentioned the 1755 earthquake to obtain tsunami travel times and tsunami wave heights. That means to read these documents for the tsunami. So she had the possibility to read 852 documents. From those 130 mentioned the tsunami. We attributed a reliability parameter to all these documents. The best are classified with R1, and the others R2 and R3. That depends on the author, the location, the time after the earthquake the document was written. And from that, we produced a set of tsunami travel times along the coast from Barbados to Azores, Madeira, UK, etc. So there is quite a lot of information. We were able to infer the polarity of the first movement. We were able to to obtain a set of run-up heights and a set of the period of the wave, the number of waves observed. That was one of the questions of the inquiry made by the Prime Minister in Portugal, was how many waves did you observe, and how long did the disturbance in the sea, the duration of the sea disturbance. So we had quite a lot of data. This was published back in 1998, so many years ago. So what we do, we don't compute sources. What we want to do is to obtain constraints on the source and not the source. So we start with the backward ray tracing simulation with all these points. This is Madeira Islands, the southwestern point in Morocco, that is Safi. And we computed the backward ray tracing simulation that gives this area along the southwest Iberian margin. And this was a solution different from the ones proposed until now that were located more or less further north and on the Orange Bank. So this was our first result. And then we selected 3 sources, and we computed the shallow water simulation with the nonlinear code. One of the solutions that we needed to test was a fault placed on the Orange Bank with a similar mechanism of the 1969 event. But we see that the radiation pattern of the tsunami, all the energy is radiated towards north-west and to the south of Morocco. There is little energy in the Gulf of Cadiz, little energy in the west coast of Portugal. Nothing goes to the Caribbean islands, and there is no energy going to the UK. So we excluded this source, and we opted for these 2 solutions. These are not focal mechanisms. These are initial displacements of the seawater that match the wave heights and the set of travel times. So either a simple source or a composite source located here is able to reproduce most of the historical observations. In meantime, and in parallel with our studies, our geologists, our colleagues started investigations on the tectonic source obtained by multi-channel seismic surveys and bathymetric surveys, and they were able to identify compressive structures related to the Eurasia-Nubia convergence. These structures are shown in this map. They are the North Orange Fault, the Marquês de Pombal Fault, the St. Vincent Fault, the Horseshoe Fault, the Cadiz Wedge, and from this set of faults, several sources for the 1755 earthquake were proposed. We don't know if they are wrong or right. Zitellini et al. Proposed one source in 2001. Then we worked with him to propose a composite source in 2003. Gutscher et al. Proposed this source, this Cadiz Wedge source, but we concluded that it gives wrong travel times to the west coast of Portugal. And finally, 10 years ago, Barca et al. Proposed a source on the Orange Bank with a strike that is perpendicular to all these faults, that he claims that it is able to reproduce the tsunami observations in the far field. So what we conclude is that the source must be there, it must be a compressive mechanism, but the source of the 1755 mechanism is still a question of debate. 6 years later, on March 31st, 1761, there was another big earthquake The earthquake was felt in Lisbon at noon, and the reports say that it alarmed the inhabitants and slowed down the ruins of the past 1755 earthquake. Documents report that a tsunami was observed as far as Cornwall, Cork in Ireland, Barbados, and the earthquake catalogs for Portugal do not have many information on this event, because apparently the Portuguese king did not want to have some noise about the problem of earthquakes, because he had the 1755 some years ago. So the earthquake catalogs located it in the Horseshoe Abyssal Plain with a magnitude 7.5, and the Caribbean catalog locates it further north at 37 north, 10 west. In this picture, we can see the previous determined epicenters, and this is the source location that we found using tsunami data. As I said, the Portuguese reports on this event are scarce when compared with the 1755 amount of data. However, in Spain, the president of the Real y Supremo Consejo de Castilla made a systematic inquiry on the event that was recently, not 20 years ago, compiled by Francisco, I think it's Francisco, no? Francisco de la Torre, and he got a quite considerable set of macroseismic intensity data. So with this data, we produced a new isoseismal map that was published back in 2006. And we were able to compile a set of 6 observations for tsunami travel times in Lisbon, Scilly Islands, close to Ireland, Barbados, in the Caribbean, and Mounts Bay and Kinsale in UK, and 4 observations of wave heights in Barbados, Penzance, Lisbon, and Kinsale. So we did the backwards ray tracing simulation, and we found this source area, this possible source area, that includes the area of the coral patch seamount. Again, we constrain the source, we don't compute the source. This was a recent work done by one of my PhD students that was recently published. So he constrained the source, the rupture mechanism with plate kinematics, and the tectonic setting of the area and the tsunami observations. And we conclude for a possible source corresponding to a compressive fault centered at 12 west and 35 north, close to coral patch seamount, and compatible with the geodynamic setting predicted by the Nouvelle 1A model. Other structures, other compressive structures were identified in this area, I believe by Sara Martinez Lorientes, that is here. And so now we have to look for the true geological source. We only put the constraints and that best match the tsunami data. So we moved to the 20th century. And the first event we looked at, it was the 25th November 1941. It was an 8.3 earthquake that occurred at 6 p.m. Madeira, Azores, and Western Portugal recorded the strongest shaking with intensity 6. The earthquake impacted the neighboring countries of Spain and Morocco. There are several compilations of the macroseismic data by Debra in Morocco, Di Filippo and Moreira, and several epicenter determinations, one of them done by Gutenberg and Victor, that also computed the magnitude, and by Professor Días with a magnitude 8.3. Here we have the location of the focal mechanism proposed by the seismologists, and these are the observation points and the tide records that we got for this event. So what we did, we had to detide to digitize, and filter all these events to isolate the tsunami signal. We studied the frequency content of these records, and we got this set of tsunami travel times. And to simulate the earthquake, we use observation points located close to these stations at depths greater than 10 meters to be able to solve the linear shallow water equations. So to do the inversion, as I said, we inverted this equation here. And this is the initial sea surface elevation produced with the earthquake focal parameters. And these here are the results of the inversion. So to check, this was the solution that we selected. And we computed, we used this one to run the shallow water model again and to see if we are able to reproduce the waveforms observed for this event. And the results are quite good, taking in consideration that these are not dart buoys, these are tide stations that are located inside harbors and have many problems that are not very good quality data. So the results of this study suggest an epicenter location at shown here. That is west of the epicenter determined by Gutenberg and Richter. However, it is important to note that both epicenters lie along this segment BC of the Gloria Fault. So the inversion of the tsunami waveforms led to a more precise location of the event. The high quality bathymetry of the Gloria Fault that is shown here, that was acquired recently, shows that the location is compatible with a change in strike of the Gloria Fault at its eastern end. So we go now to the 28th February 1969. I cannot talk about the earthquake because there are many experts here that already told everything about this event. It was the largest instrumental event with a magnitude close to 8, located in the Horseshoe Abyssal Plain. It generated a small amplitude tsunami that was recorded in Portugal, Spain, Azores, Madeira, and Canarias and Morocco. The first tide station to record the tsunami is located here in south of Portugal, and the tsunami took 33 minutes to go from this point to this point. The tsunami arrived when in ebbing tide, and the maximum was observed in close to low tide. So there are no observations of the tsunami. Of course, it was 3 o'clock in the morning, and no one was on the beach. So there are not observations on the tsunami. Of course, we should, in terms of warning, we should think that if this same event happens in August or July, where all these beaches of the Gulf of Cadiz are highly populated, a 50 centimeter tsunami requires, by international standards, the issue of a warning message. So people in civil protection need to think how to evacuate these beaches because it's not as easy as it looks like. So we did the backward ray tracing simulation. This was published in 1997 in the Journal of Geophysical Research to locate the source that is compatible with the source location obtained by seismology. We did tsunami forward simulations using, again, the nonlinear shallow water model, and we used to initiate the model, we used the solution proposed by Foucault in 1973. This gives a more or less good agreement with the tsunami travel times and the first peak amplitude recorded at the tide gauge, although the period of the waves is not so well reproduced. Now we have better models, better bathymetry, so this is in progress. This is the work I've been doing on the last weeks between my classes. So we were testing all these focal mechanisms proposed in Grandin et al. And up to now, the best match between the predicted and the observed tsunami records is this solution A, source B. I think that is the one proposed by Buffon et al. In 1988. However, we still have a problem. There is this huge negative here that it's almost 1 meter, a negative movement in the tide records of Casablanca. We had the same problem with the records of Morocco, and we don't know how to solve them. So, but any of the proposed sources is able to reproduce this negative here. So this is still something that we have to look at more carefully. The last event was the 1979, 26 May 1979. It was reported by the Portuguese newspapers. In Madeira, they say last hour maremoto, that is a tsunami, with the location of the epicenter. At the time, they gave the wrong message. They said, they told the ships to stay in the harbor when we know that the ships should go to deep ocean and not stay in harbors. But it was the message that was passed at the time. And in São Miguel, that is in the Azores, Ponta Delgada here, they say that it was observed the tsunami, and Diário dos Açores is one of the main newspapers of the islands, said that in the artificial harbor, in the old sardine pier, the sea was observed to fast withdraw, returning back and reaching the high tide water mark, and some of the boats touched the bottom of the dock. We only looked at this event back in 2008 by one of my students, Moroccan students, Fatima Kabouben. So we did the common backward ray tracing simulation, and we tested all these sources. And at the time, we concluded that the source proposed by Lines and Ruff, 1985, was the best to reproduce the tsunami observations. So the results, and almost concluding, with some provocative questions. So for the 1722, this event was previously disputed as an onshore event. We could show that its effects can be reproduced using an offshore fault, and it's the only event that was generated very close to the shore in this area, or in the north, in the Gulf of Cadiz. For the 1755, the event was previously located in the Orange Bank. It was relocated using backward ray tracing simulations of tsunami travel times, suggesting a large source in the southwest Iberian margin, and these results led to new bathymetric and seismic surveys. The 1761 was previously located in Galicia. The re-evaluation of macroseismic data by De La Torre in 1997 and backward ray tracing simulations relocated the source close to the coral patch seamount. And recently we proposed, or we constrained the source, proposing a compressive source in the area compatible with the plate kinematics, and that reproduces quite well the near field and the far field. When we mean the far field are the observations in UK and in the Caribbean islands. Now we expect the geologists to go there and find the geological source. In 1941, we were able to invert the tsunami waveforms and to compute a more precise location of the event. We use high-quality bathymetry of the Gloria fault that shows that the location is compatible with a sudden change of orientation close to the eastern end of the fault. In 1969, this is one of the best tsunami events. The forward simulation shows a good agreement with strong motion studies by Grandin, source A2. Nevertheless, the active and passive seismic research was never conclusive on the identification of the geological source. For the 1975, forward modeling and backward ray tracing led to the selection of one of the candidate sources, as I said, by Limes and Ruff in 1986, that was deduced from seismic data, and this solution is able to reproduce the first arrival, the polarity of the first movement, and the peak amplitude. And now the questions. All these events seem to be located along the borders of a lithospheric block shown in the seafloor morphology, separating pure Iberian from pure African lithosphere and deduced also from magnetic anomalies. The location of these large earthquakes is more or less coincident with the changes of the strike of the plate boundary. I will show you this draw. It's not my production. This is Miranda and Joaquim Luis' work. Here we have the magnetic isochrones, and we see that there is a sudden change in this 82 million year line that changes suddenly here, where our block seems to start. So here, these two ages are different. That shows that the lithospheric block is different. And this is still in progress, and a comparable interpretation of a block was suggested by Buffon et al. In the scope of the interpretation of the 1975 event. You cannot ask me many questions on this draw because I'm not able to answer. We leave that for the next workshop. So, questions. The events presented here are located along the border of this lithospheric block. So, shall we expect that all large magnitude earthquakes will occur there, or shall we expect big earthquakes outside this area? And this is important for the evaluation of the seismic and tsunamis hazard. What are the consequences for these evaluations? What is the geometry of this block towards west? What do we know about historic events and paleo-tsunami events in the area? We don't have any clue on the source. We only have the sediments on shore and the models to invert these, the sediments on shore to only give us the wave height. We don't have any, up to now, there are no models that could invert the sediments to the source. And why do we have these events, 3 in the 18th century and 3 in the 20th century? The 3 is a coincidence. And we have no events in the 19th century and no events previously, at least, located in this area. So I leave you with these questions.
Thank you very much, Mariana. We have a lot of time for questions and
The
comments.
questions are there, you must answer them.
Some questions? First.
No, we tried some landslide simulations, but I believe that is in the Orange Bank. Some of my colleagues tried that solution, but it does not increase the wave heights, and that does not explain some of the observations. But we don't exclude that they existed, because in 1941, there are reports of the cables, of the submarine cables that were cut offshore in Morocco. So maybe that a landslide close to Morocco might be an explanation for us not to be able to reproduce the tide gauge data for the 1941 event.
Thank you, Mariana, for your talk about earthquake and tsunami. Its summary is very good. I have a small question about the 1755 earthquake. My question
this is more
about,
difficult one.
My question is about the Grandin et al. Model of 1755. Do you test it? Because the model use directivity.
But which model?
1755.
Yes, but...
the model use the rupture process, directivity of the rupture process.
No. We
And
didn't do
I
that.
suggest to you to use the rupture process, but
A more
with
complicated
the
source,
directivity.
okay.
With the directivity.
Okay. Okay, thank you. We'll try that.
Another question from Eulalia.
Answer your question about the landslide.
She's the expert. She's looking for them, yeah.
Well, we worked in the Gulf of Cadiz since more than 10 years, and basically we mapped, actually north of the Horseshoe Abyssal Plain, there is a fault which is the Marquès de Pombal fault.
That is the one shown
yes,
there.
Okay, Marquès de Pombal is the one a little bit to the north.
This one.
Yeah, to the left. MPF, that one? Yeah. Well, there are, we mapped with a side scan sonar, and we identify part like landslide, and at the foot of the fault, we have the traces of turbidites that we could date it, and they correspond to 1755. So actually, during 1755, a landslide, it was generated there. But we tried to do simulation for a tsunami, but actually it's so thin.
Yeah.
It's just pellicular landslide, which didn't probably affect much on the tsunami.
It could affect locally, but there are no stations locally.
It was a local event, but could be related to the earthquake, to the triggering of the earthquake. Because this fault here is really steep, it's very steep, so it was easy that this landslide occurred. And then I have a question for you, which is about the source of 1755. That you on your slide you propose the sources near these sources, very near to the coast. And
they are not very near. This is the draw.
Okay. So what I'd like to mention is that in the recent paper of Sara Martinez Loriente, they suggested that the horseshoe. A potential source would be the horseshoe abyssal thrust that is published in a paper, and basically that is located within the horseshoe abyssal plain, and on the basis of seismic refraction data. And then there is a later paper by Silva that they show also a cluster of seismicity on exactly that area. What is your opinion about this potential source there?
These simulations are from 1998, so they are very old, okay? And for the implementation of the tsunami warning system, we generated a base of scenarios. And in these scenarios, we have the horseshoe fault and composite solutions of these faults to account for any scenarios that can happen in the area. But at that time, when we are producing the scenario database, it's just for warning purposes. We are not discussing if they reproduce better or not the source. We know that they can happen, and in case of an event, the warning system does an automatic search, looks for the closest scenario, and issues the warning based on that. So these are implemented in the scenario database that was produced by Matias and Rashid Omira. Not a difficult question. About 8.3 in 1941. Oops.
Yeah, you put a very good question at the end. They say, why in the 18th century and 20th century? And then...
Do you have the answer?
Yeah, and then naturally, there has to be some previous events of that time. So, what do you think about the event on the 4th century?
The 4th century.
Which is,
382?
Yeah, the 4th century. Because there is some...
Yeah, but how to relate them with the others?
The problem is about the information.
The information, yeah.
But there is enough information that was a big, because some islands were lost, and Cadiz was half...
As I said, there are many historical events that are mentioned in the catalog, but that are very easy to look with the...
And then you have also the legend about the Atlantida, which
yes,
is referred by Plato.
But I did not say that this is the end of my work. I still have some work until retirement.
Yeah,
so
I think that legend is motivated by some kind of a tsunami.
Yes. Yeah.
That,
No, there are many events, still many events that we need to look for to understand.
Yeah. And what about the event on 808 that is referred to by the Arabian historians in Spain?
But I don't think we have that one in the Portuguese
No,
catalog.
they don't mention the tsunami, but they mention the earthquake. It's very clear.
Yeah.
This is a contemporary author.
Yeah, but we didn't study that one.
And they say there was damage in Spain and Morocco.
In Spain and Morocco, maybe, yeah.
So maybe it would be good to try to study
for
that.
all. So I have plenty to do.
The problem with the one in the 4th century is that there is no Greek or Roman historians.
The 4th century is
mentioned.
quite a good question. Yeah,
But I think it would be good
to understand that one. Nevertheless, the 3 events in the 18th century and the other 3 in the 20th century maybe they are a curiosity or a simple coincidence, but.
About the 1969, in Casablanca, you said that the amplitude was negative.
Yeah, there is a negative movement there that we are not able to reproduce with any of the sources published until now.
Yeah, but maybe it's possible that because it's the mareograph.
Yes, we thought about that because the mareograph can be inverted. That is the second step we should do. But it's the largest movement. It is almost 1 meter. So it is an important movement that we should not discard. So either it is a landslide, a local landslide, either the tide record is inverted. But we didn't get access to the original one. This one is a draw that was found in Moreira's office in Lisbon.
I think that I have the...
You have the original? So we can do a paper.
I need to check.
So please check, and if it is the original, give us a copy.
Some questions or comments? So,
thank you.
Thank you for your great lecture. It was interesting, very interesting, the open question for everybody to investigate.